Of course, I have to have a good scan. How do you want me to grade your exam here? Terrible. I cannot read it. So it's obvious that you do need to send me a good quality. And you had enough time between the second exam and the final to practice and improve the quality. But don't send me pictures because I cannot write on them. Any other question? Okay. So during the weekend, I had several interesting questions, especially about biaxial bending. If you look at this formula, obviously, whenever we had a beam column, we had to have an axial load. And the axial load is on the vertical axis or the z axis. And the bending is about the x or the strong axis and the y that is the weak axis. So there are two homework problems that they have biaxial bending. So no matter what you do, either equation H11A or H11B control. And so this ratio, PU over phi, P sub N. So this is your factor axial load, this is your design strength. So everything that you can see on this left side has to do with the KL over R, the largest one control. So this is a typical design of a column. So this is the first term. And here we had the bending about the strong axis. This is M to U X magnified, but this is a strong axis. And this is phi M to M. This value, it could be equal to phi M to P, or it could be the result of lateral torsion of back. This one is the moment about the weak axis. So this moment is in the perpendicular axis. So these two, you cannot combine them because this is in the x, this is in the weak or the y axis. And this is phi m to my, the design strength about the weak axis. And I mentioned the other day because somebody asked me, or I mentioned without somebody asked me, that about the weak axis, we do not have lateral torsional buckling because the flanges, they cannot buckle like they do whenever you have bending about the strong axis. So this is the design strain about the weak axis. So I mentioned also to you that in chapter F, if you go to page 16.1-56, and I remember I did this last Wednesday, so I just want to refresh memory. Whenever we have bending about the weak axis, there are two, and only two, these are the limit states that we always consider in day one. Yielding means that your nominal strength is going to be equal to the plastic moment. Fy, this is zy, the same that there is a zx, there is a zy property of the geometry. But this has to be smaller than 1.6 Fy times the elastic modulus. And I mentioned to you the other day that if you divided this number by FYSX, it's going to give you 1.6. And that 1.6 is the reserve capacity. This is what we call the shape factor about the weak axis. That's why you can see that there's only one limit state. There is no lateral torsional buckling because the compression flange cannot buckle. So, but it could be local buckling. So this is the limit state of yielding for the weak axis, and is related to zy and xy. So whenever we solve this problem, you have to understand that for bending about the strong axis, chapter 6 assumes that V sub B is equal to 1. And also assume the magnification factor is equal to 1. For the weak axis, we do not have C sub B. It could be only equal to M sub P is more than 1.6 FYSX. So there is not C sub B in here, but there is a magnification factor for the moment about the weak axis. So both of these moments, they had a magnification factor. So what we do, we go to chapter appendix 8, the same that we did before. Appendix 8 on page 16.1, 249. And you can see in here that this formula is good for the X and the Y axis. So in the next page, this formula for the magnification factor is good for the X and the Y axis. So what it changes is that for the strong axis, this is I sub X. For the weak axis, this is I sub Y. For the strong axis, this is L sub C X, and for the weak axis, it's L sub C Y. KLX or KLY, but the formula is the same. Magnification factor for both the strong and the weak axis. And also, the way you solve this problem, whenever you have a beam column, you have to go to chapter 6. Don't go to chapter 3. It's for a beam. You have to go to chapter 3 that combines everything. In addition, something that I didn't mention the other day is just a typical section here. I'm on page 6-88. I just opened this randomly. But for instance, if you look at W12/53, in here, all of these are the phi M sub N, assuming that C sub B is equal to 1. This in here for the W12/53, these are all the phi P sub N based on KL over R, or based, you have local backlink based on local backlink. So everything that we know about beams is used on this side with the section that C sub B equal to. And everything that you know for column is used in here. But at the bottom in this table, it gives you the phi M sub N for the weak axis. So you will find for the section that you're dealing with the phi M sub N Y at the bottom of the table. And this is equal to phi M sub P or equal to phi 1.6 S X times SY times FY. So this is already computed for you. Any question? So I'm going to go over one of your homework problems because of the confusion created. Look, this is your homework problem. Like I mentioned before, right, that this is PU. You don't need to put it at the bottom, the number, because this is the same load, 140 at the top, 140 at the bottom. This in here, the 16, is KLY, KLX, and L sub B. And this is a pin, that there is a pin, so the value of K for the column is 1. So this is KLY, KLX, and L sub B. These moments, they're in a different, you cannot add these two moments because they're in two different axes, they're perpendicular to each other. So whenever you look at the moment about the x-axis, this 150 M sub UX is about this axis. So this is the tension side, this is the compression side. And whenever you look about M to U, Y is about this axis. So it's about the weak axis. And remember, we do not have lateral torsional in here. And so you have to think in terms of mechanical solids. All that we're doing is finding the state of the stresses at a point. You used to do in mechanical solid, you used to compute all the normal stresses, all the shear stresses, and after that you used to go to more circle. So we're gonna have in here the stresses produced by the bending about the strong axis, and this is on the entire cross section, force divided by area in theory. And these are the stresses produced also on this side, depending on the direction of the moment. This could be the compression, this could be the tension. So we cannot add these two more. So how do we go into the table? From here, you go to chapter 6. Chapter 6, like I said, KLY, KLX, also be the same. You go with 16. You go with M to U X and M to U Y. So you go with all of this information, you go with the largest one. So here is 150, 75. 150, 75, you go with the largest one and with KL. Any question up to this point? And the question here, find the lightest W shape. Right? So at first you had no idea. The solution, we had no idea. The point is, so there's no idea about which section will be the best section. But so we could start with a small, medium, heavy section, and from there we know where to go, to a larger or heavier, to a smaller or lighter. So we need a reference point. So we are blind right now. The only thing that we had is the 16 and this back. So to start this problem, I plotted the moment diagram about the strong axis. And so you can see that based on the direction of the moment, we had reverse curvature, compression on this side, compression on the opposite side. So all that you have to do is a simple structure analysis. And what I told you before, I already computed MA, MB, MC, but what I told you before, look, KLX, KLY, 16, that's L to C. L to BX, L to BY, 16. And so you go to chapter 6 with M to UX, L to B or L to C, and M to UY and PU. So the very first section that I tried, I went and I tried WA by 58. So this WA by 58 is on page 698. In 698. And there's no reason why I started with the W8 by 58. I just went to the table for W8 and if you look at the next table, this is the heaviest. This is the heaviest one in the WA by 58 because the next page in the next page, well, we had WA by 67 in the next page. And after that, I started the W10. So I started with the WA by 58. And the embrace length in here is equal to 16. So the WA by 58 had phi m to n 202. It had a phi m to n 418. And here at the bottom of the page, it had a phi m to n y of 105. So from this page, I got phi m to n x, phi p to n, and phi m to n y, because we have biaxial. So for WA by 58, I had a phi m to n x, phi p to n, and phi m to n y. So this comes from the table. Right now, the only thing that I need to know, I have to divide it. P to U over phi P to N, like we normally do to see which equation control. We have to go to chapter 6. So P to U over phi P to N gave me 0.33 larger than 0.2. That means that equation H11A control, and I put it in here, H11A. This information on the right-hand side, we don't need to get it right now because we don't know which section is going to work. I put it here anyway. So now that we had 0.33, this is equation H11A. Magnification factor here is assumed to be 1, assumed to be 1. So what we put in here was the 0.33, 8 over 9. This is my moment M to U over P M to NX. This is my moment M to UX over P M to NX. But when I look at this is a large number already. 0.33. This value plus that value times 8 over 9 had to be more or equal to 1. So anybody, please do the computation in here and tell me what do you get. Do the computation in here and tell me what do you get. Real quick. I'll drink my coffee. 226, right? Why I didn't do the computation? Because this was already a large number. When I look at this, look, divide 150 by 105. This by itself. What is it number 150 by 105? 143. Already went over 1. So I said, look, my conclusion was, this is too small. This section is too small. I had 226. Only this value is large, so I said, too small. But at least we had a reference. So I went to the next page, that is the next one, the largest one. This was too much. This in here was too much, so I ignored the next page, WA. In this page, the next page or previous page, WA by 67, there's no way that this is gonna make it. So I went to the W10. And I needed a W10 that was heavier than 58. So I knew that the next W8 is gonna fail. So I went to W10 by 77. Any question why I went to W10 by 77? Only reason that I did it because WA by 58 was way, way too small. So I went to the different group, W10 and with a heavy one. And I did exactly the same that I did before. Once you get to this point that you have a section that doesn't work and you try a new one, like I'm trying a W10 by 77, I go again with the same else and brace length with the same M to UX, M to UY. So W10 by 77. I obtain all of this from the W10 by 77 from the table M to NX, P M to NY, and phi P to N. Again, I did the P to U over phi P to N, 140 over 686, and this came a 0.204. H11A is still control. So I did the same. I had 0.204 A over 9, assuming 1 times M to U X over phi M to N X, M to U Y over phi M to N Y, and this came at 137. No good. So the section had to be heavier. This still is a small section. So, and also look at this value here. I say I'm going to look for a section with a larger phi M to NY. The next one that I tried was a W10 by 100. But now we had a change. P to U over phi P to N, 0.16 is smaller than 0.2. So the next equation, H11B control. This is the first time the H11B control. It means physically small P to U, large section phi P to N. Very little column option, a large moment. So this in here, the equation doesn't have the 8 over 9 and is P to U over phi P to N divided by 2. So the equation H11B, the control, these two equations, as you already know, they're very similar. For H11A, P to U over phi P to N. For H11B, P to U over phi P to N divided by 2. For H11A, all of this is multiplied by 8 over 9. For H11B, this is multiplied times 1. So we had a reversal. Now the equation H11B is controlling our design. So I did the same. This number, I divided by 2. This is 1. Magnification factor, assume 1. M to U, phi M to N X. M to U Y, phi M to N Y. 1.06. No good, but we are approaching the solution. We are getting close to the solution. If you use the solution manual, man, you find the solution immediately. But that's not the way it works. We have to approach the solution. Everybody approaches a different way. In here is what I said in the example. There are no two people that are going to have something very similar. It is impossible. So you have to be very careful in this exam. because it is impossible that you approach the problem the same way that you name. Anyway, so we are very close to the answer. So it has to be a little bit heavier. So I try W10 by 100, 112. These come from table 6. It becomes so easy that we have to be careful. Phi m to nx, design strength about the x-axis. Phi m to ny, about the weak axis, and phi p to n as a column. Again, p to u over phi p to n is smaller than 0.2, h1, 1b. Don't forget that you need to divide this by 2 because we're using h1, 1b. This is the old m to u, new phi m to nx from here. All m to u y over phi m to ny. 0.93. This is the best section so far. But I'm going to try W12 by 106 because I went up 2 instead of 1. So I want to make sure this is a good section close to 1. This is the first one that works. But I want to make sure, because it doesn't take more than 1 minute to go back to the table and check the one in between, W12 by 106. These values, again, they come from table 6 or chapter 6. So I went to a deeper section now. I finished with W10 by 112. This is the best one. So I went to the deeper section. But it has to be lighter. It has to be lighter to be a better section. I finished with the W10. I had a section that worked. So in the W12, I had to go to one that is lighter than 112. And the 106 is the next that is light. So for the W12 by 106, I forgot to mention the previous page. For W12 by 106, from chapter 6, I found phi m to x, phi n y, and phi p to n. And on the next page, I tried it. On top of the page, this is the first thing that we had to do. Again, it came smaller than 0.2 h1, 1b. Don't forget that you need to divide it by 2. This is 1. Again, this is the old m to u. This is the new phi m to nx. Assume c to be equal to 1. This is the old m to u y. This is the new phi m to ny. CB doesn't exist about the weak axis. Look, 0.85 is more than. So we went to a deeper and lighter section, and so there is still room to get close to 1. The lightest section, the best section is the one that put us close to 1. Sometimes in certain families, in certain groups or sections, this is the best one. When we try, we cannot get a better one. So sometimes the best section doesn't get you to closer to 1. Like if these were the only one, is lighter, is the best one. So sometimes we can, whenever we are able to, we try to get closer to 1. And that's what I'm trying right now to do, because we started with W12 by 106. And the W12 by 106, it looks like it's too big. a lighter one in the same group, W12 by 96. And again, this becomes very easy because we just getting the values from chapter 6. We don't have to go to any other chapter right now until we find the best section. We stay in chapter 6. One more time, H11B control. So this is a very quick computation. You have to divide this value by 2, the old M to U X, the new N VM to N X. The old M to U Y, the new VM to N Y, 0.95. Look, this is a very good section, 0.95. So right now, the W12 by 96 is the one that we're going to use up to this point. I need to go to the next family, the W14s, and I need to check one that is lighter. Otherwise, it's not going to be better than this one. And I tried the W14 by 90. Again, these values are from chapter 6. One more time, equation H11B control. We divide it by 2. This is the old value, the new value, old value, 0.88. It's smaller than. So I said maybe in this W14, 14 by 88 could work. $14 by 82, I'm trying to get closer to 1. And this comes from the table. In here, H11A is still control. And it comes to 1.28, no good. So the W14 by 90 is still the best one. Now, we could continue all the way and check all the sections in the code. But there's going to be a point where nothing else works. So we'll say this is the best one. So I need to go to the W16. W16, a lighter one. W16 by 89. And this is the same that we always get from the table in chapter 6. P sub U over phi P sub N. Now equation H11B control. So they have to be divided by 2. This is 1. The all new, all new, no good. I went to the W18, the next family, 18 by 86, and I did the same, no good. I went to W21 by 83, I cannot find another section. So nothing will work. So this is the best one, the W14 by 90. So the best one is the W14 by 9. Any question up to this point? And something that is very important in this exam, I want to see you work. Because if something all of a sudden appears, I know that it's almost impossible to get that close the first time. If something already appears in front of me when I'm grading the exam and I don't see the work, please show me your work. And we're ready to check this section. This letter F means that it had a problem as a beam. And that problem is probably the flange. I'm going to get information that I need. I'm going to check. I'm going to use the equation. So I'm going to check all of this. And I need I sub X, I sub Y. All of this information could come some information from chapter 1, some information going to come from chapter 3 from table ZX. Some information could also come from chapter 6, where we found this section. I wanted to do the magnification factors because for the weak axis, we haven't done the magnification factor. And I know that there is confusion whenever you try to solve the problem. And you look at the solution manual, sometimes you don't know where they are obtaining the number. So we do have to go to appendix number 8 for magnification factor. So this is the magnification factor. This is the formula. There's going to be one for the x-axis and one from the y-axis in this problem because we have biaxial bend. So we had to do it twice. And you have to remember that this formula for C to M, whenever we had the moment, this ratio M to 1 over M to 2 is positive when the member is bent in reverse curvature, and it's negative when it's bent in single curvature. And also, this has to be equal or larger than 1 because it is a magnification factor. It cannot be smaller than 1. By computations that you have seen before, it could be smaller than 1, but we cannot use it because it is a magnification factor. So in this problem, we're going to have one for the weak axis, one for the strong axis. So I have done in here the magnification factor for the strong axis, magnification factor for the weak axis. So you can see in here that I had computed I have put in here just to refresh your memory that is one with its transverse loading. I had done in here for both. 0.6 minus 0.4 and 1 on Earth. In our case, is reverse curvature for both of them. So the ratio between the smaller 75 and the larger 150. Is done in here. This ratio, because it's W curvature, this ratio is going to be positive or negative. M1 or M2, this ratio is double curvature, positive or negative, according to the code. Positive. So for both of them, we have 0.4. C to M is equal to 0.4. So in this formula, 0.4, 0.4. This is P to U, 140, 140. What is going to change is this value? P to E1X, P to E1Y. Pi squared is the same. 29,000 the same. This is I sub x. This is KLX. It came 7,000 for the y-axis. Pi squared 29,000. This is I sub y. And here there's a square missing. So this value, 28, 10, 64. So I put it in this formula. And for both of them came 0.41 is smaller than 1. 0.42 is more than, so the magnification factor in here, it has to be 1 because it cannot be less than 1. The magnification factor equal to 1. I need to do check as a column. And this is what I did. Turn the microphone off, please. K over R, the largest one control. It is a column, K over R Y. The largest one control. So the only thing that we need to know if there is a brace, we have to be careful because we have to check KL over RY and KL over RX. Sometimes strong axis control. For the table, at the end of chapter 4, it makes no difference which axis control. The tables at the end of chapter 4, as you already know, they're based on just a number, KL over R. So it makes no difference if KL over RX or KL over RY control, you go with the larger number. In here, it's obvious that KL over RY control, and so we went to the end of chapter 4 to the table, and we did the interpolation between 51 and 52. So we did interpolation, and the critical stress, we multiply times the area. In here, critical stress by interpolation, multiply times the area. P sub n, 978.72. Look, the table gave me 9.79. You already know that the table is great for the column portion. I did the P sub U over P sub n, 0.143 is more than 0.2, H11B. So now I had to do the beam action. Always, 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 and always for a beam. No matter if you are doing a beam column or you're doing just a beam. Always we need to know where we are with respect to L sub P and L sub R. We need to know where we are because it will tell you which equation controls. So it's very important for a beam to know your embrace length compared with L sub P and L sub R for that section. Most of the time, the equation that has L C sub B is going to be M sub P minus M sub P minus M sub R. Most of the time, it's going to control. But I have seen in the past, and I'm going to repeat what I said the other day, that look, this is a page that you already know by heart where to find. 16.147 in here, because we are between L sub P and L sub R, this is the equation that controls, so we need to compute C sub P. But this is one of the biggest problems that I find in the exam. Whenever we have this situation, this critical stress, a lot of people made a mistake. This is not the critical stress for a column. It is for a beam. So you cannot go to the end of chapter 4 because that's the column. You have to find it in here. This is where this value has to be computed. And every year, when I used to teach, I didn't teach for 3 years, I think. So this is the most common mistake that people, instead of using this, they go to the end of chapter. So be careful with it. So this is the equation that control. I need M sub P, I need M sub R, and to compute C sub B, I already did it at the beginning. I located them because total embrace length 16, from this point 4, from this point 8, from the bottom 4. But we needed to find the intersection. We needed to know where this value is equal to 0. So you can do it just by similar triangle like I did in here. We know that the equation for moment, for shear, for deflection, everything is even at the end of chapter 3. But you have to be careful when you use the formula because sometimes you get the wrong formula. So in here it's simple, but it's similar triangle. I found this value from here to here and this value also. So in here, I had computed those values by similar triangle. So C should be 2.17. This is a large number. So probably this 2.17 multiplied times this is going to exceed, it's going to exceed the value of M sub P. One question for everybody. How do I compute the C sub B for the weak axis? Anybody? How do we compute the C sub B for the weak axis? You don't have to. There not. If you do, I have to kill you. So please, there's no C sub B for the weak axis. I'm going to stop here. I'm going to continue tomorrow with this problem. It's almost done. I just want to continue tomorrow, and I'm going to solve more problems. I'm going to start the review. I'm going to continue the review on Wednesday. Any questions about anything? I know that these problems are long, but once you find a section that works, you use that as a reference. I haven't started with a review, Maria. I will start the review tomorrow and I will continue on Wednesday. But I have not started with a review. This is one of the problems that I had a lot of people asking me questions. And also, this is a problem when you have to realize that you have bending about the strong and the weak axis. Two different types of problem. And here, everything goes back to how strong your background is in mechanical solids to understand what you do. Because mechanically, we can do it, but we don't know what we do. This goes back to the state of stresses at the point. Any other question or anything? Clarification? Oh, you're welcome. So, if there are no questions, we're going to continue tomorrow. And please pay attention, especially to number 2, because the way these problems are solved, there are no two people in the planet that can solve it the same. And if it happens for the first time in my lifetime, you will be the last two in the planet that were able to do it. Okay, that's it for today. I'll see you tomorrow.